Welcome to Engineering Studio with Dr. Muhammad Tahir. In this video, we are going to solve one example for the shear design of beam. So the statement is a simply supported rectangular beam of size 300 by 525 mm having an effective depth of 450 mm carries a total factor load of 130 kN per meter. The clear span of the beam is 4.5 meter while the effective span is 4.8 meter. The flexural reinforcement consists of 8 number 25 US customary bars having the area 4080 millimeters square, 4 of which are curtailed at a distance 450 millimeters short from the face of the support. Use C20 concrete and grade 280 steel for the design of this beam. Using double leg stirrups, design the web reinforcement. We are given with a simply supported beam having span 4.5 meter and subjected to uniformly distributed load of 130 kN per meter. So the very first step is to draw the shear force and bending moment diagrams for the given beam. So we are given with the effective span as well as the clear span. So the clear span is 4.5 meter and the effective span means span from the center of support up to the center of support. From here up to here it is given as 4.8 meter. So this much distance, half of the support, this will be 0.15 meter, and similarly on this side 0.15 meter. 0.15 meter, sorry. Okay, so now we need to draw the shear force and bending moment diagram. So for shear force diagram we need to calculate the reaction at this point, and which will be equal to 312 kilonewton. So after calculating the reaction we can draw the shear force diagram, so which will be of this shape having maximum coordinate of 312 at the supports, and at the center its magnitude will be 0. And for bending moment diagram, so it will be a second degree curve with the maximum value at the center, which is equal to WL square by 8. So to calculate the value of the shear force and bending moment at different locations of the beam, we can write the equation for shear force and bending moment in terms of x. Basically, while designing for the shear, we need to calculate the shear force and bending moment first at the critical section, which is normally located at a distance d from the face of the support. So in our given beam, so the critical section will be at a distance d, and if we talk about from the center of the support, it will be 0.15 plus d, which is 450, so it will be at a distance 0.6 meter from the center of support. So x will be equal to 0.6 meter. To calculate the VU, mean the maximum shear force and bending moment diagram at the critical section. So by substituting this x 0.6 in these two equations, we can get the maximum value of shear force and bending moment, which are 234 kilonewton and 163.8 kilonewton meter respectively. Okay, after calculating the shear force and bending moment diagram at the critical section, the next step is to calculate the shear resistance of the concrete beam. So to calculate the shear resistance of the concrete, so we can use this expression, which is 0.16 lambda square root fc prime 17 rho w vu d over mu multiplied by bw d. So here this lambda is a factor which accounts for the lightweight aggregate, and in case of normal weight aggregate concrete its value is 1, and for lightweight concrete aggregate its value is 0.75. This rho w is the ratio of longitudinal reinforcement at the section where we have calculated Vu and Mu, and this Vu d over Mu, so this factor should be less than 1. So we can calculate this factor separately, Vu d over Mu. So by substituting the value, so we can get its value 0.643, which is less than 1, so it is okay. So we can use this value. And for rho w, so it is actually As over Ac, mean As divided by Bw into d. And for As, Actually, we have taken the section at a distance 0.6 meter from the center of the support. So at that location, we have only 4 bars. So we have total 8 bars in the beam, out of which 4 bars have been curtailed at a distance of 450 millimeter from the face of the support, or we can say at a distance of 0.6 meter from the center of the support. So at that section, we have only 4 bars. So because of that, we need to divide this area of the 8 bar by 2. So AS divided by 3 mean BW and D, so it will give us the longitudinal reinforcement ratio, which is 0.015. So by substituting the values in this expression, so we can get the value which is 108.7, and it should be less than 0.29 lambda fc prime square root fc prime bwd. So we can also substitute the values in this expression, and it comes out to be 175.1 kilonewton, and 108.7 is less than 175, so it's okay. So we can consider this value of 108.7 kilonewton as the shear resistance of the concrete. So after that, the next step is to check whether the shear reinforcement is required or not. So for that, first we need to calculate the design shear strength. So the nominal shear strength VC multiplied by the 5V factor. So it will give us the design shear strength, and the 5V is 0.75 in case of shear. And to check whether the shear reinforcement is required or not, we need to compare the applied shear VU with 5V VC divided by 2. So if it is more than, the applied shear is more than 5V VC divided by 2, so in that case shear reinforcement is required. So this 5V VC divided by 2 is 40.76 kilonewton, and VU is about 234 kilonewton. So this VU is more than 5V VC by 2, so it means shear reinforcement is required. Okay, so now we have decided that the shear reinforcement is required for this beam. So the next step is to calculate the shear resistance to be provided by the shear reinforcement. Mean we need to calculate this Vs, and this Vs is given by Vu minus 5V Vc divided by 5V. So Vu minus 5V Vc is equal to 152.47 kilonewton, and divided by 5V 0.75, so it comes out to be 203.3 kilonewton. Mean Vs is equal to 203.3 kilonewton. So now the next step is to compare this Vs with this factor 0.33 square root fc prime bwd to check whether the cross-sectional dimension of the beam are okay or not. So the 0.33 square root fc prime bw, if we substitute the values in this expression, so it comes out to be 199.2, and the Vs is more than this 0.33 square root fc prime bwd. But if we see, the difference is not that big, so we can consider the upper limit, which is 0.66 square root fc prime bwd, which will be double of this value 199, means it will be about 400 kilonewton. So the Vs is less than this upper limit but more than this lower limit. So if we consider the upper limit 0.66, in that case we can say that the cross-sectional dimension of the beam are okay. Or instead of changing the cross-sectional dimension, we can play with the maximum spacing or the spacing limit of the stirrups, as the Vs is more than this factor 0.33 square root fc prime. So actually we have the condition that Vs should be less than 0.66 square root fc prime bwd in any case. So if it is more than this value, then it is necessary to revise the sectional dimension. Otherwise, we can keep the same dimension if Vs is more than this value, but we can reduce the maximum limit of the spacing of stirrups. So if Vs is more than this value, so its spacing limit will be AV Fy 0.33 BW and D by 4 are 300 millimeter. But if it is less than this factor, so in that case its value will be D by 2 this will remain same. This will become d by 4 will become d by 2, and this 300 will become 600. So if Vs is more than 0.33 and the spacing limit are to be used accordingly, mean in that case, as the Vs is more than this 0.33, we will use the second option, mean d by 4 and 300 millimeter limit for the maximum spacing of the stirrups. Okay, so after checking the dimension of the beam, the next step is to decide about the bar diameter for the stirrup and the area of the stirrup. So let the diameter of the bar is number 10, US customary, mean a bar of 10 millimeter diameter. Then the area of the double leg stirrup, which is already stated in the question that use a double leg stirrup. So we are using number 10 bar for the stirrup with double leg. So in that case, the area will be equal to 142, mean area of bar times 2. So area of bar is 71 multiplied by 2, so it will be 142 millimeter square AV. Area of stirrup resisting the shear. So after that, the next step is to calculate the S required. So S required is equal to 5V area of stirrup in shear FYT D over VU minus 5V VC. So by substituting the values in this expression, we will get this S required equal to 88 millimeter. And now we need to compare this S required with the S maximum, and S maximum will be the smallest or the least of these three values. So the first condition is AVFYT over 0.35 BW. So AV is area in shear, FYT is the yield strength of the stirrup 0.3, and BW is 300, the width of the beam. So it comes out to be 379 millimeter, and as the Vs is more than 0.33 square root FC prime, so in that case the limit will be D by 4. So it is 112 millimeter, and the general minimum is 300 millimeter. So the least of these three is actually 112 millimeter, and S required should be less than this value. So S required is less than 12, mean 88 is less than 112 millimeters. So it is okay. Our required spacing is less than the S maximum. So now we need to compare this with the minimum spacing limit. So first we need to round down the value, mean we need to round down the value of 88 to 80. So S will be equal to 80 millimeter, and we need to compare it with the minimum spacing limit, which is 80 millimeters. So 80 millimeter is equal to 80 millimeters, so it means okay, our selected spacing is equal to the minimum value. If it is less than the minimum, then either we need to increase the diameter of the bar, or we need to increase the yield strength of the stirrup, or we need to increase the number of legs of the stirrups. But here in our case, it is equal to the least value or the minimum value, so it's okay. So up to here we have decided that we will use number 10 stirrup at the rate of 80 millimeter center to center for the critical section, and then we need to continue this spacing up to a certain length. And the first stirrup of this spacing will be placed at a distance S by 2 from the face of the support. So if we have a beam like this, so the very first stirrup will be provided at a distance S by 2 from the face of the support, so which is 40 millimeters. The first stirrup will be at a distance of 40 millimeter from the stirrup, and the next stirrup will be at a distance 80 millimeter. So the next question is, up to how much length we need to continue this spacing of 80 millimeter. So we need to continue this spacing up to ln by 5 or ln by 4. So ln by 5 is 900 millimeter, and ln by 4 is 1125 millimeter, mean 1.125 millimeter. So we can check that how many stirrups can be provided in between these two lengths. So 11 intervals of stirrups may be provided at a at a spacing of 80 millimeters. So if we provide 11 stirrups at a distance of 80 millimeters, so in that case the total length covered will be equal to 0.15, mean the distance from the center of support up to the face of support, the distance of the very first stirrup which is provided at a spacing of 40 millimeter, and then 11 stirrup spacing at a distance of 80 millimeters. So the total distance that will be covered by using the spacing of 80 millimeter will be 1.07 meter. So at this location we again need to calculate the VU and MU value, and we will recalculate the spacing of the stirrup, and that spacing will be continued either up to the center of the beam or up to the location where stirrups are not required. So now we can calculate the stirrups again at a distance 1.07 meters. So VU over here is 172.9 kilonewton and MU is 259.42 kilonewton, and this can be calculated by substituting the value of x in the equation that we have derived in the very first step. Okay, after calculating the VU and MU value, the next step is again to calculate VC, and here again VU and MU, by substituting these values it comes out to be 0.3, which is less than 1, and raw W is 0.3. Here it is actually 4080 divided by 300 multiplied by 450. So in the previous case we divided it with 2, but here we are not going to divide it with 2 because at this location at a distance 1.07 meter from the center of the support we have 8 longitudinal bar. So the reinforcement ratio will be calculated accordingly. So by substituting the values in this expression we can get the VC equal to 117.25 kilonewton, and it is less than 175.08 kilonewton, the upper limit. Okay, after that the next step is again to check whether the shear reinforcement is required at the new section or not. So for that we need to compare the VU, the applied shear, with the 5 VC by 2. So this is 117.25 is the nominal shear strength. If we multiply it with the 0.7 factor, so it will become design strength, and divided by 2 it will be 43.97 kilonewton. And the applied shear is about 172.9 kilonewton. So the applied shear 172.9 kilonewton is more than 43, so it means transverse reinforcement is required at a distance 1.07 meter from the center of the support. Okay, so now again we need to check whether the Vs is more than 0.33 square root Fc prime BW, or it is less than this factor. So we can calculate Vs value by VU minus 5VVC divided by 5, and then we can also calculate this 0.33 square root Fc prime BW, which is we have already calculated, which was I think 199.2 kilonewton, and we need to compare this Vs with this vector. So it is actually, we have not calculated it over here, but it is less than this value 199.2 kilonewton. So as this Vs is less than this 0.33 square root Fc prime, so it means the requirement for the maximum spacing of the stirrup will be considered like this. It will be d by 2 instead of d by 4 as we have considered in the previous case, and the general minimum will be 600 millimeter as Vs is less than 0.33 square root Fc prime BW. Anyways, so now we need to first calculate the S required. So S required can be calculated by substituting the values in this equation. So it comes out to be 152, and we can round down this value to 150. And the S maximum, it will be least of these three. So the least of these three is d by 2, which is 125 millimeter. Sorry, it is not 125 millimeter, it should be 225 millimeter. So d is actually 450, so its half will be 225 millimeter. So the S maximum is 225 millimeter, and our required spacing or selected spacing is 150 millimeter, and this 150 millimeter is less than this S maximum, so it is okay, and it is also more than the S minimum 80 millimeter, so it's also okay. Okay, so now we can continue this spacing up to the next point, or up to a point where there is no reinforcement required. So our calculated spacing is at this location is number 10 at the rate of 150 millimeter center to center. So we can provide this spacing up to the next section, or up to the point where no stirrups are required. So let's calculate the point where no stirrups are required. So to find the location after which stirrups are not required, theoretically let Vx is equal to 5VVC divided by 2. So we can equate Vu applied shear with the half of the design shear capacity of the beam. And this Vc, the shear capacity of the beam, the nominal shear capacity of the beam, can be calculated by using this simplified expression given in the ACI code. And this Vx, so we have already derived this equation in the very first step, so 312.130x, and it will be equal to 0.17 lambda square root fc prime bw, multiply it with the 5 factor and divide it with 2. So from here we can calculate the value x, which is equal to 2.10 meter. So at this location theoretically no stirrups are required. So we have already, if this is our beam, we have already placed the stirrups at a spacing of 80 millimeter up to this much length, which is from the face from the center of support up to this location, it is 1.07 meter, and at this location at a distance of 2.1 meter, beyond this point we do not need to provide the stirrups. So this much length, which is equal to 2.1 minus 1.07, so for this much length we need to provide the stirrups at a spacing of 150 millimeter, as we have calculated in the previous step. So this is about 1 meter, and if we place the stirrups at a spacing of 150 millimeters, so we can provide maximum of 7 intervals, or we can place 7 stirrups in between this location. So we can continue a spacing of 150 millimeter for 7 intervals, and extra stirrup may be provided at the center. So beyond the point, beyond this 2.1 meter, so actually our center will be over here, which is 2.25 meter. So we have this much only, about 150 millimeters, so we can provide one more stirrup at the center of the beam. So it's optional, we can provide or we can skip this. So this is the detailing, final detailing. So the very first step, stirrup will be provided at a distance of 40 millimeter, half of the calculated spacing 80 millimeter, and then we can continue this spacing of 80 millimeter up to a distance of 880 millimeter from the first stirrup, and then we can provide the 7 stirrups at the rate of 150 millimeter, and this will cover 1.05 meter, and beyond that at the center line we can also provide a stirrup. So if we cut the section at this location, so we will have 8 bars and we will have the stirrups. So this stirrup will be donated as number 10 at the rate of 80 millimeters center to center if we cut the section at this location, and if we cut the section at this location, so it will be number 10 at the rate of 150 millimeter center to center.